Alright, so I'm back with another video in the series of videos explaining Monte Carlo integration using some examples. So in this video, I'm going to work on an example where we deal with unbounded interval. And this video is going to have like two parts. So in the first part, I just go with my approach, and then in the second part, we'll work on the approach that the textbook has. So this is something that we have seen so often. We all talk about normal tables. We use them every now and then, and now we will learn how we can generate them. The code to generate them is already posted on the Blackboard in Chapter 5 folder. So let's go ahead and get started, and you can always check out the code online on the Blackboard. So we have to use Monte Carlo approach to estimate standard normal CDF, meaning, so remember, we denote the CDF or cumulative distribution function by phi of x, which is negative infinity to x 1 over square root of 2 pi e to the power minus t square. Okay, it won't let me write there. T square over 2 dt. Now we can break it into two cases. So case 1, when x is greater than or equal to 0, and case 2, when x is less than 0, and use symmetry to handle the second case. We're going to use symmetry. So we'll work on one case and then we'll use just symmetry to handle this case. So if you think of it graphically, this is your normal, standard normal curve, and let me change colors. Case 1, you're looking at negative infinity to x, this area, right? That's your case 1. Now let's change the color to something else. And another case is that it could be this area, right? So your x could be somewhere here, and then you would be looking at this area. All right. So now we have to make it work in terms of uniform 0, 1, right? So to make it work in terms of uniform 0, 1, sorry, I need to mute my phone. I forgot to do that. So to make it work in terms of uniform 0, 1, we have to use change of variable technique. Substitute y as t over x, which implies dt is x dy, and theta is 0 to 1 x e to the power negative xy square over 2 dx. So when t is 0, y is 0, and when t is x, sorry, oh, how did I do that? Okay, sorry, it's so sensitive, the screen is so sensitive, sometimes I'm still learning to work around. So y is x over x, which is 1. So our expected value of theta, sorry, the estimate of theta hat is expected value of y evaluated for this function gx. Let's call it g of x first to make it more clear. So it's g of x, which is expected value of x and y, of course. Sorry. So basically it's expected value of x e to the power minus x y square over 2. Where random variable y has uniform 0, 1, 0, 1. So one more time, so we are trying to evaluate this integral phi of x. Let me use a different color. That's the integral that we have, right? So it has an unbounded interval, and the other issue is that this x being a random variable, and x follows normal distribution, x could be here or x could be here. Like it could be greater than 0 or it could be less than 0. So we work on our case when it is greater than 0, and then we will just use symmetry to figure out the area or on the left tail, or basically cumulative distribution function when x is less than 0. So to make it work, we've been, like in previous examples you have seen that we've been using uniform 0, 1. So to make it work in terms of uniform 0, 1, you use change of variable technique. So you want your lower bound to be 0 of the integral, and the upper boundary of the integral to be 1. Right now it's negative infinity to x. So if you use this transformation, that is y equal to t over x, then when your t is 0, your y is also 0. And when your t is x, your y is 1. So that works well for us. So that means if y is t over x, dy over dt would be 1 over x, or dt is x dy. So we use this substitution as you would do in any ordinary calculus and integral evaluation. So now our theta, if you think of this as a theta, okay, that pose did not turn out to be very neat. So if you think of this thing that this integral that you're evaluating as your target parameter theta that you want to evaluate using Monte Carlo simulations. So our theta is, when we use this substitution, x e to the power negative xy whole square over 2 dx, because what you did is you replaced dt with x dy. Sorry, it should be dy. And then e to the power t is yx, so yx whole square over 2, And I forgot this 1 over square root of 2 pi. Of course it's still there. You can take that out, that's not part of the integral. Or you can use that later, like when you're done with everything, you can just bring that constant back. So that's our theta. So theta hat would be just expected value of this function g of y that we have. Okay, I should use uppercase. G of y x. If I use that, then I can. Which is this, basically the mean of this function. 1 over square root of 2 pi is still there. 1 over n sum of I goes from 1 to n x e to the power minus x u y I, which basically is your uniform 0 1 square over 2. So we are basically all set to generate the cumulative distribution functions of the left tail area probabilities. That's what people do when they generate that normal table that you have been working, you've been using for a while now, probably, hopefully. So we can write, we are ready to write a little algorithm for that. So basically the algorithm that you have to follow. Now for the code, you can check out the Blackboard, it's posted there. Once you're able to run it up, run it in your own markdown file, please do post it on discussion board if you had any difficulties, or if you figured some easier way, or if that worked, whatever happened, just write a write a small, like a 1 sentence note on the discussion board for chapter 5 that you were able to get it going, so that I'm sure that everyone is was able to get it working. So what we do is we generate IID uniform 0 1. Second step, theta hat is GNU bar, which is 1 over n sum x e to the power minus x ui whole square over 2. And of course the 1 over square root of 2 pi. When you're looking at the phi or left tail area. And then if x is greater than 0, phi x would be the 0.5 area plus theta hat. If x is less than 0, phi x is 1 minus phi of minus x. How do we get that? That's by symmetry, right? If x is less than 0, this area is same as if this is minus x. Whatever this area is, if you do 1 minus, if this area is a, 1 minus a, so the whole area is 1, you subtract that, you get this area, right? Which is by symmetry same as this area. All right, just one note. It would be simpler to generate a uniform 0 to x and skip the transformation, like I always say. Of course, x is going to be a sequence. It depends on where do you want to evaluate your phi of x. So x is basically random. So always keep in mind it would be simpler to generate random variable uniform 0x and skip transformation. Alright, so please give it a try in R. Like I said, the code is already on the Blackboard, so just use that code, or if you feel like writing a code of your own using this algorithm, please go ahead and do that. Once you have it running, post your code that is running or post your comments in the discussion box. And I'll see you in the next video.